In this video, I'm going to discuss the theory of NMR, or nuclear magnetic resonance spectroscopy. NMR is incredibly useful to organic chemists because it allows us to learn about the structure of organic molecules. Specifically, it can tell us a lot about the different functional groups present in a given molecule. While the most common types of NMR are proton and carbon, using NMR, we can study any nuclei that have either an odd number of protons or an odd atomic number, or we can study nuclei with an odd number of neutrons. Remember that the number of neutrons can be calculated by subtracting the atomic number from the mass number. Most commonly used NMR is proton NMR, which studies hydrogen, which has both a mass number and an atomic number of 1. Because hydrogen has 1 proton, an odd number, we say that it is NMR active. Additional nuclei that are NMR active include carbon-13, nitrogen-15, fluorine-19, and phosphorus-31. All of these nuclei are NMR active because they have an odd number of protons, an odd number of neutrons, or an odd number of both. These are the most common nuclei that are studied by NMR, but not the only ones that can be studied by NMR. Carbon-12 cannot be studied by NMR. It is not NMR active. Carbon-12 has 6 protons and 6 neutrons, so it has an even number of protons and an even number of neutrons, with a mass number of 12. Therefore, it is not NMR active and cannot be studied via NMR. The reason that we can study nuclei that have odd numbers of protons or neutrons is because they all have a nuclear spin. Because the nucleus is positively charged, in atoms with a nuclear spin, they are creating the movement of charge. And the movement of this charge creates a magnetic field. Therefore, each nucleus with a nuclear spin is essentially a little magnet. This can be represented by a sphere with an arrow, where the arrow is indicating the direction of the magnetic field of that specific nucleus. Of course, in any given sample, we don't have just a single nucleus with a spin. We have many, many nuclei, all with their own spins. And in the absence of any external forces, those spins can be pointing in any direction. In NMR, we take this sample of spinning nuclei, or the sample of little magnets, and we place it in an external applied, strong magnetic field. And when we place all these little magnets in this strong external magnetic field, they tend to align with the strong magnetic field. So, for example, if we apply an external magnetic field pointing in a specific direction, all of our little spinning nuclei, our little weak magnets, will align with that external magnetic field. Most of the little magnets will align with the field, but occasionally some will align opposite the field. Quantum mechanics requires that the magnets either align with or exactly opposite the external magnetic field, and there is a slight energy difference between these two states. Nuclei that align with the external magnetic field are said to be in an alpha spin state. Because these two fields are aligned, this is the lower energy of the two possible outcomes. Nuclei that line up against the external magnetic field are said to be in the beta spin state. This spin state is slightly higher in energy. The difference in energy between these two states is small but measurable, and in NMR, this is the energy difference that we're measuring. The addition of energy can cause the nucleus to flip from the alpha spin to the beta spin state. In NMR, this energy input is typically in the form of light. The amount of energy required to flip a nucleus from the alpha to the beta spin state is proportional to the external magnetic field. However, remember that these nuclei are not alone floating around in the sample. They're surrounded by the rest of the molecule and the electrons in that molecule, which can change the amount of magnetic field experienced by the nucleus and is not equal to the exact amount of the external magnetic field. Therefore, measuring the energy differences for all of the nuclei in the sample give us information about where those nuclei are in the sample relative to other functional groups. The amount of energy required to flip a nucleus from the alpha to the beta spin state is proportional to the amount of the magnetic field that it experiences. However, the amount of magnetic field experienced by each individual nucleus is not equal to the exact amount of the external magnetic field because these nuclei are not just floating freely in solution. They're part of a larger molecule, and the functional groups around that molecule and the other atoms in that molecule can affect the amount of the magnetic field experienced by every nucleus. There are other spinning charged species present in these molecules, specifically electrons. Because electrons are spinning charged species, they also create a small amount of magnetic field, and that can cause the nuclei to be shielded from the external magnetic field of the NMR. Higher electron density around a nucleus causes more shielding from the external magnetic field, and less electron density around a nucleus causes less shielding. Therefore, NMR can tell us about the chemical environment around a nucleus, because it can tell us about the amount of electron density around that nucleus, which is directly affected by the other functional groups in the molecule. Nuclei that have nearby electronegative groups will have less electron shielding because those electronegative groups pull electron density away from the nuclei. Conversely, if there aren't electronegative groups near a nucleus, it will have more electron shielding because it will have more electron density around it. Therefore, we can use the NMR spectrum to make predictions about the types of functional groups that are present near each type of nucleus that shows up in the spectrum.